Hi guys, welcome to again to my channel. My name is Madlasa. Today I'm gonna be show you a very interesting topic, which is an imperfection or a notional load analysis of a 20-story building using ETABS 2016 as per the Eurocode and Ethiopian Building Code of Standard. So before proceeding to the detailed analysis of imperfection or national lead of this story building, I will try to show you a typical example which is prepared for the clarification of the imperfection and notional load analysis of this story building. This is a tutorial part 22, which is the continuity parts of the tutorial, which is tutorial part 21, which I've already shown you regarding to the detailed design of shear walls of this 20-story building. If you are a new comer for this channel, don't forget subscribe my channel. Uh, so that you'll be getting a more relevant tutorial which have been already prepared regarding to the modeling and the analysis as well as the designing of this 20-story building using the Ethiopian Building Code of Standard and the European Building Code of Standard. So if you are a member of this channel, don't forget providing me comments and questions regarding to the designing of the reinforced concrete structures as well as the steel structures. Don't forget also press the bell icon so that you will be getting an immediate notification for videos which will be uploaded later. And don't forget sharing my video also to your friends so that your friends will be getting more relevant tutorials which have been already prepared with reference to this story building and even steel structures. So now let's proceed to the tutorial part 22, which will be focusing on the detailed exemplified works of the imperfection or national load analysis of the structure as per the Eurocode and Ethiopian Building Code of Standard. Here I have the table of content here. The table of content contains four basic contents. The first one is which will be focusing on the types of imperfections that we are going to consider during the designing of high-rise building. So those imperfections are that is the geometrical imperfections, and the second imperfection problem that we will be facing is that is the material imperfection, and the third one is which is the structural imperfection, which will be focusing in detail. The second topic will be that is the analysis of the imperfections in structures. So that is in reinforced concrete structures as well as in steel structures. And the third one is the types of the imperfection, that is the global imperfection analysis for frames. And finally, we will see the solved examples. Okay, here the term imperfection is used to describe the problem of accuracies or the problem of the straightness of the member during the construction of the structures, or it is the term which is used to the problem of imperfection regarding to the fabrication of the materials. Basically, this uh, this imperfection in a structure can be described as It is a deviation and inconsistencies in structures and structural members, which can affect the behavior of the structure from the theoretically assumed perfect data. Meaning, every structure has its own defined cross section or its own defined mechanical properties or its own defined the verticality geometry. So, from the theoretical assumed perfect states, there may be a change during the fabrication of the material or during the erection of the member. So, imperfections in structures are often investigated during analysis, and their effects are taken into consideration, especially in cases where they could be critical. So, we need to consider the problem of imperfection during the design of the high-rise structures. So also, when a two-story framed building that is supposed to be perfectly straight or vertical is leaning, that means we may have a G plus 2 structure here. We may have a G plus 2 structure. So this structure may be leaning by 3 degrees, just like this. So such kind of leaning, what you call it is geometric imperfection. So this form of geometric imperfection is taken into account when analyzing a sensitive structure. So we can model this column as if it is inclined by 3 degrees and this column as if it is inclined by 3 degrees. So the leaning or the swayness of the structure will be taken directly into our model so that the imperfection due to the geometry will be considered uh, automatically in during the analysis and designing of the structure. Uh, Here we have three types of imperfection. The first one is that is the geometric imperfection, uh, which results from the change in geometry. And the second one is it is the material imperfection, which result in the change in the mechanical properties of the material. And the third one is the structural imperfection, which result in due to the problem of centricity or plumpness or problem of the shifting of the supporters. So we will see in detail one by one. The first one is that is the geometrical imperfection. So the geometrical imperfection meaning as the implies there are imperfection due to variance in dimension of the member or lack of straightness or verticality in structural member. Meaning if we have a column here having a cross section of uh, that is 300 by 300, suppose this is a column. So initially we may design a column having 300 by 300 cross-section size. But unfortunately during the construction the size may be reduced to 290 by 290. So there is a reduction of sizes due to the problem of workmanship or due to the problem of formwork. So this kind of problem of geometrical imperfection can be accommodated during the design of the structure. So, as this implies, thus are imperfection due to variance in dimensions. Means just the cross sections may be reduced during the construction, or lack of straightness or verticality in structural member. That means we may have a column. So this column may be leaning to some angle. It may be 3 degrees or it may be 2 degrees. So during the erection of the column, the column may not be straight or vertical. So it may be tilted at some angle. So due to the problem of the erection of the formwork or the workmanship problem. So this kind of uh, imperfection problem can be regarded as geometrical imperfection. So, for example, when a beam member that is supposed to be 400 millimeter depth and finished as 395 millimeter, then this is a geometric imperfection because the cross section is reduced. According to clause 5.21p of Eurocode, deviation in members cross section is normally taken into account in material partial factor of safety. So the geometrical imperfection can be accommodated or can be accounted by using the material partial factor of safety. That means for concrete, that is gamma of concrete, which is equal to, it is 1.5, and for steel it is 1.15. So thus partial factor of safety will account the problem of the geometrical imperfection. So all thus factor of or partial factor of safety will be used during the definition of the properties of the concrete and steel. And the second types of imperfection is the material imperfection. So what does material imperfection mean? So this type of imperfection always arises from deviation in the assumed material property. So the mechanical, it depends on the change in mechanical properties of the material. Actually, if we use M34 design, so during construction, we should use M30 grade of concrete. But unfortunately, the grade of concrete comes 28.5 megapascal. So this is due to the problem of mixing, or this may be due to the quality problem of ingredient material. So this kind of material imperfection has to be accounted or taken into consideration during the design of the member. So then this is a material imperfection. Also, when the modulus of elasticity is the another mechanical properties of the concrete or steel, which is 200 kilonewton per millimeter square, and unfortunately, during the compliance test, it comes around 195 kilonewton per millimeter square was fabricated. So this is also a material imperfection. Another variance in material imperfection is residual stresses. So which occur in a steel member during the welding of the fabrication. So in general, the material imperfection is the problem which will be happening during the fabrication of the construction materials. So in order to take into account the material imperfection, we need to introduce the introduce the material factor of safety, just like that of the geometric imperfection. So geometric and material imperfection can be taken into consideration by using the material factor of safety in our design. So the third one is, which is the basic and the critical imperfection problem, is this structural imperfection. So what does structural imperfection mean? So it is nothing but it arises in structure due to issues like eccentricity in joints, uh, variation in supports or boundary conditions, variation in stiffness or rotation of joints. So this what you call it is structural imperfection. So there may be some eccentricity of joints. Suppose, for example, if we have a column, so here if we have a column, just this column, here the center of the column is just this one. So this column may be tilted at some angle during the erection of the formwork. So this one. So here the center of the column will be shifted from one point to the other point. So there may be an eccentricity initially. The load is assumed to be acted at this point, but due to the structural eccentricity problem, the load there is some eccentricity problem A. So just issue like eccentricity in joints and variation in support or the boundary condition. So the support may be shifted from this point to this point. So there may be a shifting of support, variation in stiffness or rotation of joints. So all those structural imperfection will be accounted during the design of the structural member. And so analysis of imperfections in structure. So in frames, all type of imperfection are usually introduced as equivalent geometrical imperfection with increased value of amplitude. While in plated structure, geometric imperfections and residual stresses are introduced to derive the buckling factor. According to clause 5.3.1 of Eurocode, the following imperfection should be taken into account. The first one is the global imperfection, and the second one is the local imperfection. So the global imperfection is nothing but its effect is global for the building of the structure, and the local imperfection uh, is the problem of one member. So suppose we may have a column. So we may have a column. So there is problem of imperfection. And if we have many columns, so this is what we call it is global imperfection, because the effect is it is global. So there is leaning of, that is phi for this, and for this there is this phi. So for local imperfection affects the single column, but global imperfection affects the whole structure. So global imperfection for frames or press systems cover for lack of verticality. For frames or straightness of the structure restrained by pressing, while local imperfection cover for lack of straightness or flatness of a member for a single member. So this is for a single member, and global imperfection is for the whole member. Imperfection may be determined from this formula. So the Ethiopian Building Code of Standard and the European Building Code of Standard specified in the code to use the fraction value phi, which will be used to calculate the equivalent horizontal forces or the notional forces during the analysis of the structure. So this phi value equals to phi naught times alpha h times alpha m, where this alpha naught is, it is the basic value, which is 1 over to 100, meaning which is 0.5%. And here we have alpha h it is the height, the reduction factor, which is associated with the height of the story. That means alpha h it is the reduction factor for height applicable to columns, or it may be for walls. And alpha m it is the reduction factor for number of columns in a row. So using this formula, we can calculate phi. And also alpha m it is a reduction factor for the number of columns, and it can be calculated with this formula. So the value of alpha h should not be less than 0.67, and it should not exceed 1. So it is between 0.67 and 1. If alpha h is less than 0.67, so we need to take this value. If it exceeds 1, so we need to take 1. So we need to be take care while we are calculating the alpha h, because we need to take h is the height of the story, which is measured in meter. So here alpha m is so when we take alpha m, so this is the maximum. It is the maximum number of columns in a row. So, for example, if we have this structure, suppose we have a column here, we have a column here, we have a column here, and we have a column here. We have a column here. So, alpha m, which is alpha m, maybe in x direction. So, alpha m in x direction, suppose we have this one. So, alpha m in x direction is here. Alpha m for this axis it is 3, for this axis it is 3, for this axis it is 4, and for this axis it is 4. So if this is the first floor, suppose it is first floor plan, so alpha mx equals to, how much is it? It is 4, because this axis contains maximum number of columns in a row. So alpha m may be taken 4 for x direction. For y direction, here we have 2 here, and we have 4 here, and we have 4 here, and we have 4 here. So how many number of columns in a row? That is the maximum number of column in a row is, it is 4. So alpha my will be, how much is it? It is 4. So alpha m I depends on the maximum number of columns in a row with a specified story. So the maximum number of columns in a row at every stories for every direction should be taken critically. So a schematic diagram showing the representation of sway imperfection with equivalent horizontal load is shown below. So the imperfection problem will be represented by the equivalent horizontal forces. So the problem of imperfection will be represented by, or will be accounted by, applying the equivalent horizontal forces to the center of mass of our building at every specified floors. Suppose here we have the G plus 2 building. We have a gravity force, that is V1, V2, and V3. So there is sway imperfection in this structure. So due to the sway imperfection, the structure is shifting just like this. So it moves laterally with an angle of what? It is phi. So this imperfection will be accommodated by applying an equivalent horizontal force at every stories. Here, the imperfection, the equivalent horizontal force is, that is equivalent horizontal force, that is the notional load. It is the notional load. It is a fraction of the vertical load. So previously we have seen how to calculate phi value, and here Vi is, it is a story gravity force which is applied at every stories. So this value, just values can be obtained from manual calculation or from ETABS. So corresponding equivalent horizontal loading to account for sway imperfection. So we need to apply a lateral force at every stories. So now, according to clause 5.3.24b, building frames sway imperfections may be disregarded whenever HED is greater than 0.15 VED. That means it is factored load. So we need to apply the factored gravity forces at every floor. So when the total horizontal force greater than 15% of the total gravity force, so in that case, no, we should not apply the equivalent horizontal force. The equivalent horizontal force must be applied in order to account the problem of imperfection if and only if the total horizontal force applied on our structure is less than the 15% of the total gravity load applied at every stories. So in order to so here I have the spreadsheet which I have already prepared for the detailed analysis of the imperfection load for this story building. So here we have the just now let me come to here. Here I have the 20-story building data here. So here this one is, it is the lateral force which is obtained from the static analysis for every story, and here I have the story gravity force which is obtained from the ETABS. And here I have also I can calculate the 15% of the total gravity forces of the every story here, just like this. So finally I can check whether imperfection is required or not for every story by using this formula, just like this. If H2, that means that is 15% of the total gravity force at every story greater than the total lateral force which will be applied at every story, then in this case we need to consider the notional load, because the 15% of VED is greater than that of the total lateral force applied at every story's center of mass. So here, this can be obtained from the ETABS. Now let me show you. So just in order to calculate the lateral force which will be applied to the center of mass of every floors, uh, just go to the display menu here, just story display plot. Then I need to make it. So here, that means the lateral force which will be applied at center of mass of every stories can be obtained from ETABS. Just here I can take EQX or EQY because EQX plus and EQX minus EQY plus and EQY minus are the same because the lateral force calculation depends on the story mass. So the story mass in all directions are the same. So that is why the lateral forces are the same for all directions. So we can take from the table, from this table here, that is 67, 200, yeah, 67, 229, 346. So all these are the lateral force which will be applied at every stories. So the lateral force, the lateral force which will be applied at every level uh, is less than that of the 50% of the gravity load. That is the gravity load, which is the story gravity load. So in that case, we need to consider the imperfection. So here, the story gravity force can be calculated from also ETABS. So this data can be obtained from ETABS. So how can we obtain it? Just go to table, the story force, just go to results and structural results. So just simply go to the story forces, that is the gravity forces. Here so I need to make it the load combination, which is the factor the gravity load, this one. And here I need to consider the bottom part. Here, this is the total gravity force. That is 24, 64, 14, 0, 60. Now let me come back to it here. That is 24. And this is the total gravity force of every floor. Okay, 24, 64, 24, 64, 40, 0, 60, 40, 0, 60, for 16 story, for 15 story, that is 30,681, 30,081. So just in similar way, we can calculate the total story gravity force of every floors using ETABS 2016. So we can put this value here, and we can calculate the 15% of the total story gravity force, and we can compare this value with the total lateral force in order to determine whether the consideration of notional load is required or not. So this is how we can determine whether the notional load or the imperfection load will be considered in our structure or not. Okay. So here this V1, V2, V3 is nothing but it is the value of the story gravity forces, which will be obtained from ETABS. And phi is nothing but it will be calculated using the formula that is this is nothing but it can be calculated using phi, which is equal to phi, that is the basic sway angle, times alpha h, which is the reduction factor for height, and times alpha m. So after calculating phi, we can multiply this the story gravity force with this value in order to obtain the story lateral forces. That means the equivalent horizontal forces. So uh, we can calculate alpha m for every story. That is, for this, it will be alpha m1 for this, alpha, sorry, that is phi1, and for this, it is phi2, and for this, it is phi3. So, phi will be different for every floors because it depends on the number of the columns per row and the height of the story. However, the basic sway angle is uniform for all stories. So this is just how we can calculate or how we can decide whether notional load consideration is required or not. So imperfection load case in load combination. So we need to take a care while we are combining the imperfection load with the gravity and the lateral load. So the direction of the notional load. How can we apply the notional load in our structure? So this depend on the direction of the lateral force, such as the wind and the seismic, which is applied on our structure. So dead load, live load, the load and live load are applied in our imperfection load case in load combination. That means uh, in all the combination we can apply the dead load and the live load. That means that is the dead load plus the live load plus the imperfection load. That is the national load, that is dead, plus the national load, the notional load live. So this is this is one of the combination of the notional load with the gravity load. However, we have specified we have to specify its direction. That is notional load. It may be in x or it may be in y direction, or notional load in x or in y direction. So the notional load, as we have already said, notional load is a fraction of the gravity load. That means the live load and the dead load, keeping that the direction is similar. That is for live load. That is, if we take the fraction of live load in x direction, so we need to take a fraction of dead load in x direction for just calculating the notional load. Therefore, load combination which contains lateral load, imperfection load case in the same direction as the lateral load. So, the direction of the notional load or the imperfection load is along the direction of the lateral load, which is the seismic load or the wind load. For example, in the case of this one here, the wind is acting in y direction. So, we need to apply the notional load along y direction. And in this case, here the wind load is acting in x direction. So we need to apply the notional load along in x direction. So the notional load has to be applied at center of mass. or at center of gravity. Here, center of mass or center of gravity. So, if we apply also the seismic load, that means earthquake load, EQY in this direction, so the notional load has to be applied along y direction. And if we apply also, that means EQX in this direction, so the notional load or the imperfection load will be applied along the direction of seismic load. That means along x direction. So the direction of the notional load has to be consistent with the direction of wind or the direction of seismic. In the case of gravity load combination, the directions of the notional load will be in x, in y, in negative x, and in positive x directions. That means x negative, x positive, y minus, and y plus. So we have four directions for the gravity load combinations. That means in order to for gravity load combination, that is the dead load plus the live load plus notional dead load x plus notional live load x. And similarly, we can make this x minus, and we can make this also x minus, and we can make this also y plus, and this one is y plus, and we can make y minus and y minus. So generally, how many gravity load combinations we will have? For gravity load combinations of notional load. When we apply a notional load in outer way, the notional load will be applied at center of mass or center of gravity of every floor level automatically after defining it. So we can apply the notional load in two ways. One, manual application. That means just calculating equivalent horizontal force which depends on V times V, or we can use automatic application. So in the case of automatic application, we can use software. So in this case, the notional load will be applied at center of mass or at center of gravity of every floors. Now let me show you how to apply the manual and the automatic way in this two-story building. Suppose here we have this structure. We have this structure, so just go to the define menu. Now let me show you the how to apply the notional load in automatic way. Just that is load pattern. Here we have the notional load in here. For example, the notional load dead load in x positive direction here. Notional load dead in x positive. That is more modified. Notional load x positive. Yeah, that is dead. This is the notional load in x positive direction with reference to the dead load. Here we have a dead load, and here we have the phi angle, and here in y direction we can apply in this way. So dead load, which is multiplied with, that is 5%, will provide the notional load in x direction, and here also the dead load in y direction. Here that is it is the phi value. So the phi value multiplied with the dead load will provide the notional load along y direction, and here also the notional load in y direction with reference to the live load applied on the floor. That means that is 0.05 multiplied with this load. This live load will provide the notional load along the y direction. And here the notional load for live load also in x direction. Here the notional load for live load in x direction, which is 0.05 multiplied with the live load which is applied at the floor. That is, this will be will provide the notional load along x direction with reference to the live load. And here also the notional load for vehicles, that means for parking. So this will provide also here in x direction the notional load in x direction with reference to the parking load is just 0.05 multiplied with what? This vehicle load, that is 5 kN per meter square. So it will provide the notional load along in x direction with reference to the vehicle load. And also in y direction also we need to apply the notional load in y direction with reference to what? The vehicle load, that is 5% multiplied with this live load. And similarly for the notional load for roof live load. Here the notional load along x direction due to the live load for roof is 5% of the live load which is applied at the roof. So it will provide the notional load along x direction with reference to what? The live load for roof. And the live load for and similarly we can define in y direction. And the notional load along x direction due to the wall load is just like this. That is, here this is the direction of the notional load, and this is the phi value, and this is the dead load. So just like in this way, we can define the notional load both in x and in y direction for every load cases. So ETABS will take all those loads, and finally those loads will be applied at center of mass. When we apply the notional load manually as nodal force HF, the HF will be applied at nodes of vertical members. That means at columns or at shear walls. So when we use manual method, so we need to apply the equivalent horizontal force at nodes of every columns. And here this is just a table showing the way how to combine the notional load with the gravity and lateral force. Here, this is the Here we have the dead load combination. Here this is the dead load combination. All those are dead load combination, meaning 1.35 dead load plus notional load in x direction. This is in x direction, and this one is in minus x direction, and this one is in positive y direction, and this one is in negative y direction. That means this is dead load. So 1.35 dead load plus 1 times notional load in x direction. That means this is the notional dead load, and this one is also notional dead load in x minus direction, and this one is 1 times notional dead load in y positive direction, and this one is the notional dead load in y minus direction. So here there is the dead load here, and when we come to the combination factor, so the dead load here, the notional load, the factor for the notional load in x positive direction is 1.35, and in negative x direction it is minus 1.35. So 1.35 times the dead load will provide the notional load in x positive direction, and 1.35 multiplied with the dead load will provide the notional load in negative x direction. And similarly, the notional load in this is in 0 degree, that is along x direction, and this is the notional load in 90 degree, that means along y direction. Here this is along the y direction. Here this is for positive y, and this is for y negative. That means 1.35 times the dead load, this dead load 1.35 times the dead load will provide the notional load along the y positive direction, and similarly 1.35 multiplied with the dead load, this dead load will provide the notional load along the negative y direction. So we'll have for gravity load combination here. That means 2 in positive direction and 2 in negative direction. And also here we have also another combination that is 1.35 times the dead load. Here we are taking only the dead load. We are ignoring the effects of the imperfection. So we do have 5 combination. 4 combination involving the notional load, and the other is excluding the notional load. So this is for only the dead load combination, and the other is for dead load and live load combination. So here we'll have also for combination. So this is gravity load plus live load plus notional load. So here we have in x direction, this one is x direction. So in x positive, that is 1.35 multiplied with the dead load plus 1.35 multiplied with the live load in x direction. This one is in x direction. Here this is 0 and this is 0, which is similar direction. So this is in x positive direction. So 1.35 dead load plus 1.5 live load plus 1.35 dead load plus 1.5 live load will provide one of the combination, and the other in negative x direction, that is 1.35 dead load plus 1.5 times the live load in x minus direction. This is x minus direction plus 1.35 dead load plus 1.5 live load will provide the second combination. And the third combination will be along y direction, that is this is y plus and this is y minus. So 1.35 live load plus 1.35 dead load plus 1.5 live load along y positive direction plus 1.35 dead load plus 1.5 live load will provide the third combination. And the fourth combination will be in negative y direction minus, that is 1.35 dead load plus 1.5 live load plus 1.35 dead load plus 1.5 live load will provide the fourth combination. So all those are the notional load factor, the factor by which we are going to multiply the dead load and the live load in order to obtain the notional load. And also the other is, here we have how many combination are there? We have 4 combination. Here we have 5 combination. Here we have 4 combination plus this one. Totally we have 5 combination. Here this combination is also considered by ignoring the imperfection load. Only the live load and the dead load combination factors are taken into account. So here we don't have any notional load. So in this case 1.35 dead load plus 1.5 live load will be taken into consideration. And the other is, that is the lateral load combination. Here in the case of lateral load combination, we'll have how many combination are there? 8 combination. That means here we have this formula. That means gamma times G plus gamma times Qi plus phi 0 times gamma times Qj in x positive and x negative direction plus or minus notional load, notional dead load in x direction plus or minus notional load of live load in x direction. That is, this is for live and this is for what? For dead. So generally, how many combinations are there? Here we have 4 combinations. That is, 2 combination in positive direction and 2 combination in negative direction. How it comes? That is for leading condition. For leading condition, suppose the live load is leading. Here, this one will be, it is what? 1.5 times 1.5 times the live load Q, and this will be phi 0, that is here phi, it is 0.7 for office and residential building, and phi 0 which is equal to 0.6 for wind. So suppose if this is the front live load and this will be the wind load, so here this is what? 0.6, that is 0.6 times gamma, that is 1.5. How much is it? It is, how much is it? 0.6, that is 0.9. So 0.9 multiplied with the wind in what? In x positive direction. So this is one of the combination in x direction, that is x positive. But here we'll have also the wind load will be the leading one. So in that case, this 1.5, this will come to this, that is 1.5 wind in x positive direction plus, that is the floor live load, that is 1.5 multiplied with 0.7, that is times, that is what? Q. So here that is in positive direction, and this one is also in positive direction. So how many combinations are there? In x positive direction, the combination. So in x positive direction, we'll have two combination. In x negative direction, we'll have two combination. Totally, four combination will be obtained. So here, and in y direction also, similarly, we'll have four combination. Totally, we'll have how many combinations are there? That is eight combinations. So eight combinations will be generated. So here uh, the we'll have two combination for leading and two combination for accompanying variable actions. So here uh, that is the notional load combination factors for the live load is it is 1.35. That means 1.35 times the dead load. I mean 1.35 times the dead load in what? In x positive direction. And here we'll have also 1.5 in x positive direction, but this is for live load and this is for dead load. And here this is the normal live load and this is for the notional load. That is the live load for notional load and this is the dead load for notional load. And this is the independent live load. And here we have also what? It is the wind, that is 0.9. Here, in this case, the leading one is what? It is front live load. It is the leading one. And this is the accompanying one. This is the accompanying one. So this is one of the combination. And when the wind load is the leading, that is 1.5, it becomes 1.5 and it becomes 1.05. And here the floor live load is here, it is the leading one. And here the wind load is, it is accompanying one. That is in which direction? Which is in, that is in minus x direction. So in positive x direction, we'll have two combination. In negative x direction, we'll have two combinations. So totally, how many combinations are there? In x direction, that is four combination. And similarly, in y positive direction, here, in y positive direction, sorry, uh, this is for, that is for x direction, x positive, and this one is also, that is x positive direction. So in this case, here, sorry, okay, the notional load for the live load here, this is the notional load for live, this is the notional load for live in x positive direction. Okay. This is in that is in x minus direction. This is in x minus direction, and this one is in x positive direction. That is, this is 0 degree, and this is the live for x positive direction. This is the live load for x. This is the live load for x positive direction. This is x positive. So this is also the live load for x negative. This is for x negative. And this one is x negative for dead load. This is for dead load and this is for live load. And when we come to the for wind, just we can apply in similar manner as we have already applied in x direction. So for y direction, we can follow the same procedure. So totally, how many combinations are there? That is 8 combinations. We'll have 8 combination and so 4 in this case and 4 in this case. Generally 8 combinations are required. So this is for the gravity and lateral load combinations of the notional load. And here, sorry, and for the seismic load combination, here it is for dead load. This is live load, and this one is the live load. I mean the dead load. Here, this is dead load. That is G, and this one is live, and this one is dead, and this one is live, and this one is live, and this one is live load. So here, uh, generally, the uh, the seismic load combination formula looks like this one. That is the gravity load plus psi 2 times the variable load plus earthquake load in x direction. That means this earthquake load in x direction is represented by this formula. That is plus or minus EQX plus or minus 0.3 EQY plus the notional load with reference to the dead load in x direction plus or minus the notional load with reference to the live load in x direction. So here we have how many combination? That is 8 combination can be generated. How it comes? Simply, that is the plus sign will have 2 combination, in minus sign we'll have 2 combination. Here in this case we'll have 4 combination, and also in y direction, here in y direction also, here the plus sign will have 2 combination and the minus sign will have 2 combination. Generally here we'll have 4 combination and here we'll have 4 combination. So generally we'll have 8 combination. So now let me write the first 4 combination along x direction. That means keeping that this is here G plus psi 2 psi 2 is 0.3 for office building times Q plus EQ, that is EQ X plus 0.3 EQ Y, this one, and here EQ X minus 0.3, and here minus EQX plus 0.3 EQY, and here plus minus EQX minus 0.3 EQY. How many combination? Also 4 combination. So in similar way we can also generate 4 combination along y direction. So 8 combination will be generated. So for every combination we need to define the notional load here plus we are applying the notional load in x direction. So the direction of the notional load must be consistent with the direction of the seismic load. That is plus the notional load in x direction plus that is the notional load with reference to the load in x direction plus the notional load with reference to the live load in x direction. And in the case of here, this is it is the plus sign. We'll have also the second plus sign here, so we can repeat this one. What is what differs is this one. And also similarly in minus, that is in negative x direction. So we can here we can make this plus sign into negative sign. That is minus the notional load times the notional load with reference to the dead load in x minus direction minus the notional load with reference to the live load in x minus direction. And we can repeat this one again. So we'll have also what? For combination. So we can apply the same procedure for y direction. So generally we'll have 8 seismic load combinations of notional load. So all those are the combination factors for the notional load. Here, this is the dead load and this is the live load. And what is here? This is all those are the notional load HF. Here, this one. This is the combination factor for notional load HF. So here, the dead load, we need to take 100% of the dead load for the notional load. That is the notional load with reference to the dead load in x direction plus the notional load with reference to the live load in x direction here, and plus the seismic load in x direction x. So we should not combine the seismic load. Here we have also 0.3 AY, here 0.3 AY, and we have 0.3 AY. We can put this one, this combination, because 30% of the seismic load will be coming in y direction, while 100% of the seismic load is applying in x direction. And similarly here, that is 0.3. Here we have 0.3. So 30% of the seismic load along x direction will be combined with 100% of the seismic load coming along the y direction. And in this case also, in minus the seismic load along the negative x direction will be combined with the 30% of the seismic load along the y direction. Okay, 0.3. Here this is minus, and so this is the positive, and this one is minus, and this one is positive, and this one is minus. And when we come to here also, that is plus 0.3, and here minus 0.3. So generally we'll have how many combinations are there? 8 combination will be generated. So what we are going to take into account is the notional load or the equivalent horizontal force will be applied for every seismic combinations. But here we'll have this is the live load factor, that is 0.3 for seismic, and this is for live load in x, and this is the live load in y. That is the notional load with reference to the live load in y direction. This is 0.3. And also here the notional load, the equivalent horizontal load must be applied with the similar directions of the live load. Here the direction dead load x must be combined with, that is dead load. The notional dead load X should be combined with the notional live load X, that is with the similar direction. And also here AX. And when we come to also the live load, here the notional load with reference to the dead load in y direction must be combined with the notional load with reference to the live load in y direction. So similar directions must be combined. And also here, just in similar way, the notional load due to the dead load in x direction, in x positive direction, should be combined with the notional load due to the live load in x positive direction. This one. So when we come to also y direction, must be combined with y direction, and x direction must be combined with x direction. This one. Here. This one with this one, and this one with this one. And also similarly, if this is in x direction, we need to combine it with seismic load in x direction. And if this is in y direction, so we need to combine it with seismic load in this is in y direction, will be combined with the seismic load in y direction. Which is that is in x direction, x. So sorry, here this is written in a wrong way. So this has to be just come to this one. So this value 1 must be written here 1. So here this is in x direction, and this one it has to come to here. And in a reverse way 0.3 has to be written here, and the y direction, this is okay here, this is y and this is y, so this has to be combined with this one, and this has to be in x, has to be combined with this one. So now let me clarify once again. Okay, now this is how to combine the notional load with the seismic load. So here this x direction, this is the notional load, all those are the combination factor for notional load, for the dead load and the live load, and also this must be combined with the seismic load in x and in y direction. So here the notional load with reference to the dead load in x direction, and the notional load with reference to the live load in x direction must be combined with the seismic load in x direction. That is good. This must be combined with this one, all those. And similarly in y direction, the notional load with reference to the dead load in y direction, and the notional load with reference to the live load in y direction must be combined with the seismic load in y direction. So it must be written here. This was written wrongly because the notional load must be applied on the direction which is parallel to what? The seismic load. And here this is also, that is x direction, and it has to come to here, that is 1. So this must be 0.3, this one instead, and here 0.3, And when we come to here also, it is so here the notional load in y direction, that is in y direction, so this is okay. That is, it has to be combined with the seismic load in y direction. And when we come to also the load in a negative x direction, here the notional load with reference to live load in x negative direction, it has to be applied combined with the seismic load in x direction. That is good. It is okay. And similarly, in negative y direction, here in negative y direction, the notional load with reference to the live load, it has to be combined with the negative x direction. Negative x, no negative x, this has to be written here. Minus. This minus, this is the notional load in y direction, that is minus 1. In negative y direction, and here the level for notional load in negative y direction has to be combined with the seismic load in y direction. It has to be minus 1 here, and this must be what? It is 0.1. Sorry. And when we come to here also in negative x, x, and this one minus 1 here, and this one is it is 0.3. It is 0.3, and also minus y, it is okay. That is 0.3 here. So this is y, and this is y, and this is minus, and this is x minus, and this one is also minus, and this one is here. This one is minus. Okay, and when we come to here, this is x, this is okay, and this is y, and this is y. That is this is 0.3, and this is 0.3. So, and this one is x positive here. This is 1, and this is minus 0.3, because I have already used the positive 0.3 here. And when we come to y positive here, it is okay, but this one is 0.3. So this is that is y, and when we come to here, minus x, that is 0.3, and when we come to here, minus 1, that is minus 0.3 plus 0.3 here, and when we come to on the y direction, that is minus 0.3, here this is y direction, and this is minus 1, it's okay. But here we have minus 1 here, and here we have minus 1 here. This is minus 0.3, this is positive 0.3. Okay, so we can combine just like this. So the notional load in x direction must be combined with the seismic load in x direction, and the notional load in y direction must be combined with the seismic load in y direction. So it can be corrected just like this. This is the general formula. This is the dead load, and this is the live load, and this is the seismic load. So here Now table for the imperfection check. It provides check table to show how factored load is applied to imperfection load. So the following table shows the application of imperfection load is required if 50% of the axial force is greater than the horizontal force. That means the horizontal force, if the horizontal force is greater than 50% of the vertical force, then in this case no application of notional load. So just ignore notional load. And if the horizontal force is less than 50% of the vertical force, so notional load will be considered. So this is one of the example. Here this is the example we shows how to calculate the horizontal force and how to calculate the axial force and how to calculate the 50% of the axial force and here the imperfection check. So this is the load combination. So for a specified load combination, and the horizontal force in x direction is just this one, and in y direction is just this one. I have already shown you how to extract this horizontal force, and the axial force is this one, which is the governing critical axial load. And just we can calculate the horizontal force and compare it with the axial force. So if this row exceeds this value, also in that case, we need to apply the axial force. I mean the notional load. So here this is the imperfection check. So imperfection load consideration is required because the horizontal force is less than 50% of the axial force in all the cases. And now fraction of the notional load in different codes. So the fraction of notional load in ASCE 7 will be just 1% of the gravity load. And in ISCC 360, the fraction of the notional load is between 0.2 and 0.3%. And in Australian standard, the value of phi is the value of phi is how much is it? That is phi, which is it is 0.2. In the case of the Australian, and in the case of Netherlands, it is phi, which is equal to what? It is 0.2%. And in the case of British standard, it is 0.5%. Which is phi value, and in the case of Eurocode, the national laws that can it is variable, but the maximum value is it is 0.5. So the phi should be less than 0.5%. So we can take the maximum value 0.5. And when we come to also this example, here, the nodal load generation for the imperfection load. Here, this one is a typical column. So this is the axial load, which is obtained from structural analysis. So here we have phi 1 for the last story, and phi 2 for this story, and phi 3 for this story. So here the lateral load which will be applied at the top of this story will be phi 1 times P1. P1 is this axial load. And for the lower story, that is phi 1 times P1, this one will be acting in opposite direction. And here we have also the lateral load, which will be applied at this story, that is phi 2 times P2. So the net lateral load which will be applied at the story will be equal to the difference of the two. That means this minus this one. And when we come to this also, we can calculate in similar manner, that is phi 2 P2, which will be coming from the top. The lateral load which will be applied at this story, which is the cumulative axial load, that is P3 times Q3, uh, less phi 2 times P2, which is the difference will be what? The lateral load which will be applied at this story. And at the base of the story, there will be the, the shear force, which will counteracting the the lateral load, that is Q3 times P3, this one. So in this way, we can calculate the modal lateral load which will be applied at the top of every story. So here the maximum axial load must be taken from the critical member having the maximum axial load at its base and apply for all member with respective story. That means, now let me show you here. Uh, so here this is the maximum axial load at the base of the wall B1. So wall B1 is the critical vertical member having a maximum axial load at its base. So I have already taken it is axial load done for the calculation of the phi value. So the phi value will be calculated based on this axial load. This axial load will be applied for the last 17th story, and this axial load will be applied for columns which is located at 16th story, and this axial load will be applied for the calculation of phi value for the fifth stories. So just extracting the axial load for all the columns will be tedious. That is why just I am taking the critical axial load which is obtained from the critical member. So here phi value will be here it is 0.05, just because the phi value should not exceed 0.05. So here the maximum value will be 0.05 because the actual result exceeds 0.05. That is why I'm taking the maximum value. And here for 16th story, the phi value will be 0.0466, and for this one 0.0042. And in y direction, the phi value will be this one, and here the 16th story is this one, and for the 70th the fifth the 15th story is this one. So accordingly I can calculate the lateral load that along in x direction, that is, where is it, this one, VED multiplied with phi value. This phi value will provide 0.535, and for y direction also 0.50553, and this is the lateral load which will be applied at the top of the 70th story. And here I have also uh, the uh, the lateral load which will be uh, applied at the top of the 16th story here, just in both in x and in y direction. So this is the cumulative value. So this is the cumulative value. It is the cumulative value. So we need to calculate the nodal force at the every nodes of the column here. So it is 0.535 for the x direction, and for y direction it is 0.50. Just we can take as it is, but when we come to here, in x direction, this minus this, this minus this one, because we need to, we should not take the cumulative lateral force. And so we need to take the historic lateral force. And when we come to also in the y direction, so here in the y direction, this minus this, which is 4.85. And when we come to also the 15th story here, just this, this minus this will provide this value. That is the modal force. Just like this. This is the 70th story. And here, this modal force will be how much? This is in x direction, suppose. So how much is it? It is 0.535. 0.535 kilonewton. And at 16th story, how much is it? It is 4.82. 4.82. How it comes? 4.82. That is 5.35. 5.35 minus this one, 0.535. 535. So it provided this one. And when we come to also the 50th story here, the 50th story, this value will be 7.2 minus 5.35. So 5.35, this value. That is 7.28. Sorry, this is x direction. 7.4 minus 5.3. 7.4 minus 5.5. Sorry. So it provides 2.08. So just like this, we can calculate the nodal force at every nodes of every columns at a specified stories. So here finally, so in this way we can calculate the nodal force which will be applied at the nodes of every column. Just like this here. This one. This is the axial load, and this one is the imperfection load, which is calculated based on the provided phi value. Here phi is for 0.01 for this one, and 0.002 for this one, and 0.003 for this one, and 0.004 for this one, and 0.05 for this one. Sorry, 0.02. 0.05 for this one. So using this value, we can multiply the vertical load with phi value in order to obtain the equivalent horizontal force. So here, this is the final nodal force which will be applied at the nodes of every column. Like this. And here, this one is the reaction force, which is the summation of all those forces. So, this force will not be applied in the model. So, the only nodal force which are going to be applied in the model are those forces. So, this is for one column. So, for all the rest of columns, in similar way, we can apply the nodal force. So, here, this is the story, the name of the story, and this is the height, and this is the number of columns in x and in y direction. That means here at the first story, here at the base at the first story, here we have 12 number of column in x direction and 12 column in y direction. So here finally all those nodal forces will be applied on every nodes of the column based on the calculated modal force results. So this is all about for today. Next time I will be showing you how to apply the imperfection load on the specified 20-story building using ETABS 2060 as per the Ethiopian and the European building code of standard. So this is all about the principle of the notional or the imperfection load that should be considered during the analysis and designing of the high-rise building. So if you like my video, don't forget sharing to your friends so that your friends will be getting more relevant tutorial which have been already prepared for the modeling and designing of this 20-story building. And if you want to get a new notification, so you can press the bell icon in my channel so that you will be receiving a notification while I will be uploading new videos. Even you can get a notification for the previously uploaded videos. And if you have questions regarding to the designing of the high-rise reinforced concrete structure as well as the steel structures, so don't hesitate providing me comments in my commenting box, so that I will be answering your questions within a short period of time as much as possible. So this is all about for tutorial part 22, which is focusing on the notional or the imperfection load based on the Ethiopian Building Code of Standard and the European Building Code of Standard. So see you next time with the detailed analysis and calculation of the notional load of the 20-story building based on the Ethiopian Building Code of Standard and European Building Code of Standard. So bye bye.